norm, you have completeness relative to the norm. That's characteristic of these. All these are complete in the appropriate norm. The norms all look like this. You just take the squares of the components, add them all up, take the square root. That's the norm of the vector. 17-dimensional space, so there was 17 components. Each squared, add it up, make the square root. So if you have one of those beasts, you can do this, which isn't in the book either. But I just thought I'd bring this up. A simple function is a function that has a finite range. So I can make a simple function by taking a Banach space value. So beta sub I is a complicated object. It can be a 37-dimensional vector in a vector space that's complete relative to the norm. Beta sub I is Banach value. You know, like we have real value and complex value. This is a Banach space vector. It can even be an infinite dimensional space, the one that they do quantum mechanics. Horrendously, potentially complicated object, beta sub I. And I multiply that by the characteristic function chi of EI. EI is the set upon which the simple function is to assume the value beta I. A simple function is one that has a finite range. A simple function is a step function that's allowed to, or that has a finite support. A simple function is a step function that's captured in a finite domain. The only difference between simple and step is the step. The Heaviside function is a step function, right? It comes in from minus infinity to 0, hops up 1 unit, goes out to plus infinity. And if you chop that off somewhere so that it has finite domain, it's a simple function. So we like simple functions. They have bounded support. So we make a Banach valued function this way. The n values of the beta i's, and then multiply that by the characteristic function of the set EI, upon which the function has the value beta I. You know what the characteristic function is? Chi, right? Chi of x is 1 if x is in the set, 0 if it's out of the set. It's the indicator function. See? So I have made this s of x here is a Banach value simple function. Okay, great. I'm defining the integral of that to be just the value beta I, which is Banach, times the measure of the set EI. Okay? Remember, the set EI is in the measure space, so it has some notion of mass associated with it. So I take that and multiply it by the Banach value beta I, and then I add them all up over all the EIs. So the beta i's are finite, the mu's of the EIs are finite because it's a simple function, it's bounded there, the domain is bounded. That's called the Bach-Kerr integral. That's a fairly recent object. This is an integral. You don't get a real number out of this, you get a Banach value out of it. Okay? And, all right, that's great. So we have Bach-Kerr integrability of simple functions. We'd like more general functions. So what we do is the usual deal. We sneak up on a more general function with a sequence of simple functions. That's a standard operating procedure. We have a sequence of simple functions that convert to a general function. So this thing here is an ordinary. It kind of got split. Sorry about that. It's an ordinary Lebesgue integral because the norm of a vector is just a real number. So this is a regular Lebesgue integral. This is the regular Lebesgue integral. F is the general function, and this is the sequence that's sneaking up on it. If the integral over the set that we're interested in of the norm of the difference between the general and the special one as n goes to infinity, so the sequence is moving up through the function, right? You'd expect this to get smaller and smaller because these things converge to this in the vector space. If the integral is 0, then you say that the Bachner integral, the limit of the Bachner integrals of the simple functions is the Bachner integral of the general function. Run that one by Penn. I'm sure you'll impress him. Because that's a fairly recent invention by a guy by the name of Salomon Bachner. So here, with the assistance of the Lebesgue integral, you can integrate in a space that's very much different from just finding the area under a curve. Right? We're way out there. This could be an infinite dimensional space where wave functions and quantum mechanics live, and where we're having sequences of simple functions converging to them. It can be really way out there. Okay? All right. So I'll stop talking about that. The last thing I want to do tonight is talk briefly about the Henstock, Kurzweil, Heron, Denjoy, McShane, can't think of anybody else, integral. And that one, oh, that's the Danielle thing. And I sort of stopped writing definitions there because I wanted to go over it. I'll add to that, unless you're offended by it. All right. So, now we're at the top of the heap. I like the way Burke says, the Riemann integral was good enough for the 19th century. The Lebesgue integral was good enough for the 20th century. We need something for the 21st century. It's got to be the Henstock-Kurzweil, which weirdly is a throwback to the Riemann construction. The Henstock-Kurzweil integral will integrate the Dirichlet function. Remember, the Riemann integral and the Cauchy integral, they all failed doing that. You're stuck on either side of it. You can't do anything. The great idea of the Henstock-Kurzweil approach is to come up with what's called a mesh function. The mesh function customizes the partition for the function that you're trying to integrate. So let's have a go and see if we can do the Henstock-Kurzweil integral of Dirichlet. I might get lost, but you know. This is my 5th hour talking. Well, I'm here. Josh talked earlier. Okay. So, the Henstock-Kurzweil sums will look just like Riemann sums, except the partitions will be chosen so that you get convergence where there used to be none. Let me just see if I can explain this. So remember, this is the function we're looking at. It's a 1 if x is in rationals, and 0 if it's irrational. So this thing is vibrating back and forth infinitely often here because the rational is dense. So to try to get around it on either side with some maximum or minimum or infinite soup thing, it just isn't going to work. So here's what we do. We enumerate the rational numbers. And it doesn't matter in what order we enumerate, but they are enumerable, right? We have R1, R2, RK. Is it clear that the contribution sum of a tag point that's irrational would be 0. So if we have a partition that has an irrational point, remember, at an irrational point, the function is 0. So that particular, if we have a subinterval with an irrational number as the tag point, we get nothing.